let's look at the Math 198 Cardiac Output Lab, created by Melissa Stoner. In this lab, we're going to use basic calculus and basic derivatives, along with some basic algebra, to understand a little bit how the heart works and to model blood flow and, well, cardiac output. First, what we're going to do is we're going to get to know our terms. You can pause the video, read the paragraph right over here. Gets into all the different terms: cardiac output, heart rate, stroke volume, ejection fraction, and diastolic volume, and systolic volume. You want to take a sec to read, maybe reread, and really know this very well because we're going to be referencing these guys a lot. So here are the equations that are given. And let's take a sec to dissect this a little bit, right? Because we have our first equation, which is that cardiac output equals the heart rate times systolic volume. All right, that's right. Or sorry, stroke volume. But then note that, I'll just write equation 2 here. This is the same thing as saying heart rate times, and instead of stroke volume, right, we have this equation right here, right? So we can substitute in this guy, right? Those two guys, right? Which are ejection fraction and diastolic volume, right? And then further, just want to point out that we also have, we won't use it right now, but we're just going to have it here just for when we do use it, or maybe when you use it, that we can substitute ejection fraction as follows, right? We have heart rate times, and instead of ejection fraction, we have, this lovely fraction right here. But then that's being multiplied by diastolic volume. And so we see that they cancel. And so this is actually heart rate times N diastolic volume minus N systolic volume. Okay. Now, we're going to focus for this video, we're going to focus a lot on equation 2, or maybe call it, I would say equation 2 or function 2, however you want to call it. We're going to represent cardiac output as a product of heart rate, ejection fraction, and systolic volume. And then later on, after the video, you will need to maybe continue using it that way, or possibly number 3. Okay. So if you want to pause the video really quickly and take a look at this notation and such, in particular, note the units, right? Actually, on the first page here, they do have a set of units right here. So just get used to those units, and in particular, remember, we're going to be multiplying things, maybe even dividing when we take the derivative. So just be a little used to those units, right? And sometimes the best way to get used to them is just to dive on into the math and just start doing stuff and see what works and what doesn't, right? So here this says express cardiac output as a volume of HR heart rate with the patient parameters above. So first off, let's recall that, right, equation 2 said that cardiac output equaled heart rate times, I think we had ejection volume and then diastolic volume, or no, sorry, it was the ejection fraction is what it was. Times that, right? But since CO is going to be cardiac output is going to be a function of heart rate's going to be the variable. So let's put this ejection fraction and diastolic volume at the beginning and put heart rate at the end, right? Because that's the variable. And just noting that they give you these parameters and it's in terms of milliliters. And they say, well, no, I actually want you to convert it to deciliters, right? This guy right here. Okay. Right, so if you think about it, a milliliter is 1,000th of a liter. A deciliter is 1/10 of a liter. So we're multiplying it by 100. We're multiplying, I guess you could say, EDV by 100. Now we're, or I guess rather you could say, I guess we're going to be dividing by 100, I suppose, right? So we have that. So we're going to be using these guys instead. Okay. So we just plug these in and we get 60% or 0.6 times 1 deciliter times HR. And another way to write this is 0.6 HR. And when we're working with the numbers, we don't necessarily need to work with the units, but just be aware that heart rate is beats per minute, and and diastolic volume is deciliters. So we are talking. So what are the units here? It is deciliters per beat per minute, or 0.6 HR deciliters times beats per minute, however you want to think about it, okay? So now they say find the cardiac output if HR equals 80 beats per minute. Well, that's easy enough. We just say, okay, CO equals 0.6 HR, and we're just going to plug in HR equals 80. Right, so you can do that, right? We just get 0.6 times 80, and no tricks over here. We're going to get 48. And just remember, our units are deciliters per beats per minute. Actually, Dr. Stoner likes to write beats per min, so we'll write it that way, okay? Now we get into some calculus, right? That was all just algebra, right? Just creating a function, plugging stuff in. Now we talk about calculus, right? Find the instantaneous rate of change of CO with respect to HR. Now, they give you a value of HR, but hold on a second. If you think about it, if CO equals 0.6 HR, well, what's the derivative? It's just 0.6, right? It's just a constant, right? This was a linear function. So the derivative is just the slope of the line. Okay? Now, just to point out, if we were being more general, if we had that CO equaled EF times EDV times HR, then you would say, oh, actually, sorry, I forgot to, I should say derivative of CO with respect to HR equals this. So I should have written that. Then in general, the derivative of cardiac output with respect to heart rate is going to be ejection fraction times end diastolic volume. Right? So it's just that. Okay. And really you could just say for all values of HR. Okay. Now, one last question though is what are the units for the derivative? Well, you think of the units as you do with division, right? The derivative is really a limit of a quotient. So, if you take a look at the rate of change, they actually do have the units, right? If cardiac output is deciliters per minute and heart rate is beats per minute, then the minutes cancel out and you're just left with deciliters per beat. Okay, so that's actually our units here. And that's worth noting. Okay. All right, so number 4, use your derivative to predict CO if heart rate changes. Well, first of all, we know the function for cardiac output, right? We know that. So on the one hand, I'll do this on the side. I'll do this in blue because this is not what we're supposed to be doing. I'll say A CO of CO just equals in general 0.6 times HR. And so if we're plugging in HR equals 40, then we're going to get 0.6 times 40, and that's, I don't even know what that is, but it's 24, I think. 24, and then what is that? Beats per minute, was it deciliters? Beats per minute, right? And then similarly, of course, we could say, oh, you know, I'm just gonna copy paste this because it's the same thing, right? Just duplicate this, right? Right, but here we're plugging in 120, right? And so we just get a slightly different value. I think it's 72, yeah. It's just 72. Right, okay, but that's not really what the question's asking us. Like, yes, you could do this. Yes, it's pretty straightforward. But they say use your derivative. Okay, so let's do it. So this is a quick little application of linear approximation, right? We can say, okay, if you remember the linearization of a function, right? Normally we write L of x, but I'm just going to use HR instead of x. This is going to be f of x, which will be CO of HR, plus, and then this is going to be the derivative. You could call it CO prime, or you could call it dCO over dHR. And then this is going to be times HR minus our nice value over here, right? So actually, let me rephrase. This shouldn't be D over HR, right? We should be plugging in our nice value. This should be 80. And then this should be 80 right here. Okay? And when we do this out, right, and this is also, by the way, HR equals 80, right? So when we do this out, we're getting CO of 80. What did we say? That was 48, I believe, right? Right up here. Yeah, 48. This was 48. The derivative was 0.6. And we had HR minus 80. Okay. So then, if we want to know what happens at 40, we just plug in 40. And what do we get? Well, we get 48 plus 0.6, 0.6 times negative 40, and was that negative 24? Same as we got over here, right? So in this case, the approximation was actually exact because our function was a line. Okay. And so we have a similar thing over here. I'm going to ask you to try that. Go ahead and try part B. You know what you're supposed to get. So just do the same methodology as in part A and see what you get. Now we're going to go ahead and do a similar sort of thing, really an analogous sort of thing, except we're expressing cardiac output as a function of end diastolic volume, not heart rate. Heart rate is now going to be a constant. Ejection fraction is still going to be a constant. EDV is going to be our variable, right? So again, we know, using equation 2 from way above, that we have, I guess we wrote it as heart rate times ejection fraction times EDV. But since cardiac output is a function of EDV, let's just emphasize that these guys are constants and this is our variable. And now if we're going to use the patient parameters above, well, I guess that's 80 times 0.6 EDV, and I think we said that was 48 EDV. Now, again, maybe you want to pause for a second, take a look at the units. Actually, I guess that's just the, that doesn't state the unit. This says the units. But remember, cardiac output is always deciliters per minute. Okay. So now if we look at the cardiac output, for EDV equals 1, well, pretty sure we just get 48. And again, our units are deciliters per minute. Okay. All right, so now at this point, finding the instantaneous rate of change of the cardiac output with respect to EDV, and they say if EDV equals 1 deciliter, but, you know, if CO at this point equals 48 EDV, well, then that implies that derivative of cardiac output with respect to end-diastolic volume is going to be 48. Now, what are the units going to be? Well, remember that cardiac output was deciliters per minute, and that EDV, what was the units for that? It was deciliters. So really, we just have 1 over minutes. It's really just, in other words, it's just per minute. What? Yeah, just 48 per minute. Okay. Now you might say 48 what per minute? Well, it's actually dimensionless per minute, which is kind of nice because it doesn't matter what your units are. You always get 48 per minute. Okay. Now, use your derivative to predict cardiac output if EDV changes. So again, I'll do part A, you do part B. We're going to say that the linearization of cardiac output using EDV is going to equal cardiac output of, what was our special value, 1, plus the derivative when EDV was 1, right? Yeah. Times EDV minus 1. And so when we do this out, we're going to get, was that 48? Yeah, it's 48. 48 plus, and our derivative was, well, again, it was 48, right? We have that. So, linearization of 1.5 is just going to be 48 plus 48 times 1.5 minus 1. And that equals 48 plus 48 times 0.5. And I think we see that that's 72. Right? And what should this be? Well, it's the same unit as cardiac output, right? So it's deciliters per minute. Okay? As for part B, you've got this. All right. Let's take a look at maybe one more example. Maybe I'll do one more. Okay, we're going to express cardiac output now as a function of ejection fraction. Now, remember, ejection fraction is really effectively dimensionless, right? It's a percent, but it's not really a unit. It's not like milliliters or beats per minute or something like that, okay? So anyway, if we're going to express cardiac output as a function of ejection fraction, well, let's remember what we're expressing cardiac output as before. And again, rewrite things so that our variable is on the outside. And then with the parameters listed above, right, with HR equal 80, EDV equaling 1 deciliter, because again, we convert to deciliters. We're going to get, again, I'm just getting 80 EF, right? Now remember that EF is just a percentage, so that's not really a unit. Heart rate is beats per minute. EDV is deciliters. So we again have, right, they say deciliters per minute. Right, deciliters per minute. Okay. So we have that. So to find cardiac output, if EF equals 60%, which is really just 0.6, we say, okay, cardiac output is 80 EF. If EF equals 60% or 0.6, we're just going to get 80 times 0.6. And that's just a nice way of saying 48. And again, 48 what? Deciliters per minute. All right, so I'm going to leave you to do this guy, but it should be very similar to what we did before. Very similar to what we did before. And then try these guys too. Just want to point out that for this one, we do need to use the equation, or the function, cardiac output equals, and I believe it was EDV minus ESV times, I think it was times heart rate. Let me double check that. I want to make sure I gave you the right equation. Yeah. I put the heart rate first, but yeah. This guy, right? So for the last one, you're using that guy. There you go. All right. So try to complete this by the next class. You've got this.